Okay, so we're going to talk about a 2 kilowatt CO2. Now, 2 kilowatt CO2s or multi-kilowatt CO2s are very common in industry. They're what we call sort of a workhorse laser of the industrial industry. And a 2 kilowatt CO2 may be a laser cutter, it could be a welder, it could be a heat treater, and when we say a cutter or a welder, that's for metals or non-metals. A very versatile laser, a great heat source, and we can get high power out of it. So this one is 2 kilowatts, it's 10.6 microns. So let's use microns here. Be a little easier to input it. So we'll say 10.6. Continuous wave is 2 kilowatts, so we could put 2 e to the 3 or 2,000, and then the system will correct it to scientific notation, or change it to, edit it to scientific notation. Should have stopped while I was ahead. The ANSI default for the far infrared is 10 seconds. The ANSI default for accidental or unintentional exposure is 10 seconds. So we'll be using that. We will be using 1 over e squared, circular Gaussian. The beam diameter is 18 millimeters, and we have a beam divergence of 1.5 milliradians. And that's pretty typical for a multi-kilowatt CO2 at or around 2 kilowatts. Let's put our observer range at 0.5 meter. I'm going to go ahead and adjust both observer ranges. We'll put this at 1/4 meter. We'll start with that anyway. And what I want to do is take a look at what happens to the OD at observer range for a large beam. Okay, well, you'll notice that the OD at observer range is less than the worst case OD. The worst case OD says, yep, we're going to put all that 2,000 watts through the limiting aperture and determine the OD from that. But realistically, an 18 millimeter diameter beam will not fit through the limiting aperture of 3.5 millimeters. And 3.5 millimeters is the diameter of the limiting aperture for the far infrared. Right. So how much power will pass through the limiting aperture if the beam diameter is 18 millimeters and the limiting aperture is 3.5? Well, about 7.2%, and that equates to 145 watts. So the average power or radiance in the limiting aperture is 145 watts divided by the area of the limiting aperture, which is 0.096. Notice that the skin limiting aperture is the same, okay, for as the eye limiting aperture, and that's because the absorber is the same. The absorber for this wavelength, this long wavelength, far infrared, is water. So this beam would get absorbed right at the getting absorbed right at the surface of your cornea, and the same for your skin, right at the surface of the skin. So you'll notice that the MPEs are the same. The ocular MPE is 0.1 watts per square centimeter, and the skin MPE is 0.1 watts per square centimeter. Okay, so everything that we see with the eye will be duplicated for the skin. All right. Okay, so we see that by the time we take the power through the limiting aperture, divide it by the area of the limiting aperture, that gives us the average power irradiance of this laser, which is about 1.5 kilowatts per square centimeter. That is compared to the MPE, and then we take the common log if it's larger, and we get an OD of 4.179. Okay, now if we take a look at the skin MPE, it's the same as the ocular MPE. The times skin MPE here is about 15,000 times. So the irradiance of the laser is about 15,000 times the skin MPE. So I think we could go ahead and say this is probably going to be a skin hazard. As a matter of fact, this is going to be a severe skin hazard. If you put your hand in this beam, or accidentally get your hand in this beam, or your arm in this beam, you're going to really notice it very quickly. Okay, and it's not going to be a life-threatening injury, but it will make an impression. You won't do it anytime again soon. All right, because that is really gonna hurt. Okay, a laser like this, if you put a piece of wood in front of it, you're gonna get a flame jumping off of that wood in no time. It's something we say about eyewear. Eyewear for this laser is clear. It's just polycarbonate, although let me say right now you can't just use polycarbonate shop glasses per se, because they must be marked with the wavelength and the OD if it's being used as laser eyewear. Doesn't mean you can't use a pair of shop protective eyewear, the polycarbonate protective eyewear or shop eyewear. It's just that the LSO would have to mark it for it to be used as laser protective eyewear. Okay, but we often say that if you're wearing your polycarbonate laser safety eyewear and you get struck in the eyewear by a beam like this, you will get a noticeable, visible signal that something is happening, because there will be a flame kind of come off that eyewear. That will be your first warning that you need to move. Okay, so yeah, this is why we report the times skin MPE, because in some cases, like with high power lasers, particularly UV lasers, we're going to really want to take a look at this times skin MPE so we get a good idea of what kind of hazard are we talking about in terms of this particular output interacting with our biological tissue, our skin. Okay, and as we can see, this is going to be a severe skin hazard. Okay, now the NOHD for this particular laser is 1.51 kilometers, and since it's the same limiting aperture and same MPE, we would expect the NSHD to be the same, and it is. Okay, let's take a look at the diffuse reflection hazard here. We're going to say 100% of the light is reflecting off. Since there's no such thing as source type here, remember we're out in the far infrared, we're well outside the retinal hazard region, so there's no such thing as source type. We'll keep our diffuse reflection at 600 seconds. We'll keep this default small beam on target, quarter of a meter away. We can see that our ocular MPE is the same as our intrabeam diffuse MPE, both for skin and the eye is the same for the intrabeam MPEs. And that's because, well, for 10 seconds and 600 seconds all the way out to 30,000 seconds, the MPE is the same. Okay, the NHC is about 0.8 meters, where if we said our observer is a quarter meter away from the diffuse reflection, the observer would need an OD eyewear of at least 0.1. We have the same skin NHC as we do the ocular NHC, and we have a times skin MPE for the diffuse reflection. It's about 10 times, so this is a significant hazard for a diffuse reflection from this if we're that close to it. Now, we already know how far back we need to be, and typically for large CO2s, these are industrial lasers, even if we're using a partially open beam cutting system, which means that between the cutting head and the material, that's going to be open, and that's the reason we look at the diffuse reflection here. Your observer is going to be at least probably a meter away from that. So let's put 1 meter in for here. Now, would we recommend OD for the operator for a partially open beam CO2 cutter running 2 kilowatts, even though it says that we don't need an OD if they're 1 meter away? Yet no, we would recommend eyewear anyway. Okay, because it's possible that if the cutting machine gets a little close, whatever, the operator leans in to adjust something. We want to make sure, and when I say lean in to adjust something while it's running. That's a common thing for an operator to do, particularly on older machines. So we always want the operator running a high power, partially open beam cutting system to be wearing eyewear. Okay, but it does tell us that it's not the diffuse reflection hazard for CO2 isn't as bad as what we will see some diffuse reflection hazards, and that's because the MPE is not as restrictive as compared to other wavelengths, which we can take a look at a little more at that later. Now, more realistically, if this machine is cutting and it's coupling into the material and actually cutting, you're probably getting something like between 10 and 20% of the energy scattering off. So if we wanted to adjust that, we would say, well, let's put 20% in, and you can see how the NHC gets reduced down to less than 0.4 meters, or less than half of what we originally had when we were looking at 100%. Okay, so you can always adjust that, and for a system that is cutting, you will get about 10 to 20%, no more than 20%. And I actually, most of the time when it's big CO2 is cutting, it's around 10% that it's diffusely reflecting off. If it were to lose the coupling into the material, then of course it would be much higher. And so most of the time we set this 100% to take a look at it, at what the diffuse hazard would be. Before we leave this, I want to talk about one more issue with it, and that is, a lot of times in these big machines we do some maintenance and then maybe even do some servicing where we're going to open the laser up fully. We'll be looking at an open class 4 beam. We may be doing something with the output coupler. We may need to tune it up. We need to let the beam propagate a little bit, and when we tune it up, we tend to tune these up at full power, or at least start out at low power but then touch them up at full power. And so when this happens, this machine may have been sitting on a shop floor and didn't need barriers around it, but once we open this up, we need to create a temporary class 4 control area. And what we're going to want to know is, what barrier do we need? How do we ask for the barrier for this machine? So that's what this little box is right down here. This little box is about giving us the irradiance of the beam, the irradiance based on this beam diameter, not going through a limiting aperture, because barriers, when they're tested, they're spec'd out based on the beam diameter used. But that beam diameter is in 1 over E. Notice that this is in 1 over E squared. Okay, so this particular irradiance value here, which is irradiance in 1 over E squared, is based on this diameter, but this diameter divided by the square root of 2, and of course we want it in centimeters, so instead of 18 millimeters, we'd use 1.8 centimeters. We divide it by the square root of 2, and then calculate the area based on that diameter, and then divide that into 2,000 watts, and you'll get your irradiance right here in 1 over E squared. But as I said, the barriers, we're really looking for irradiance in 1 over E because, again, even for barriers, we're talking about peak irradiance. So all we have to do is come right here and click this and get 1 over E. And you can see what happens is when you move from 1 over E squared to 1 over E, it just simply doubles the irradiance. This irradiance is twice what the 1 over E squared irradiance is. And if you think about it for a little while, you can probably figure out why. Think about that square root of 2 and squaring it. Okay, let's go back to 1 over E, because right now we're saying, well, wait a minute, that's based on the observer range. Where's your barrier going to be? Well, we're going to put these barriers up, and we're going to say it's the barriers will be about 2.5 meters away. Remember, we're defining a closed-in area here for a temporary class 4 control area. So these barriers would be about 2, let's say we know that we'll set them up about 2.5 meters away. So we're going to spec it at that. So we put 2.5 meters in here. Then we look at this, and you see, yeah, it went down a little bit. That's because the beam really didn't grow that much. It didn't get that much bigger, but it did get a little larger. So the irradiance in the beam in 1 over E did go down a bit, but this so we need a barrier that can withstand 1.5 kilowatts per square centimeter, and this is what we would tell our barrier vendor if we're trying to buy a set of barriers. Now, what I think a better way of doing it is do the calculation, look at it yourself, but then hand the parameters to the vendor, tell them how far you're barrier is away, let the vendor calculate it and see if you calculate the same thing. It's just a good way to make sure everybody's on the same page. And then the vendor will recommend which barrier you want to put up for this particular unit. But that's what this box really is. It's about being able to calculate things in using the beam diameter, and in particular, this is a great little box for calculating barrier irradiances if we need to know that. Now, what if we were working with something that is pulsing? We would want to know not only the irradiance, but if it's single pulse, we would only get the radiant exposure in joules per square centimeter. You'll notice if we select it here, nothing comes up. Okay. But if we were pulsing, we would have these values also in radiant exposure, joules per square centimeter. So we would hand that to the vendor. Would want to know that too, because you want to know the average power, power irradiance for in the beam, and also the radiant exposure. So all right, that takes care of that. And let's see, before I move away, when we start looking at lens-on-laser and fiber optic, we can get the same information about the irradiance and radiant exposure by looking at the beam diameter and not looking through the limiting aperture. We can get that information from this little box also. If, for example, the CO2, once it's running, we say, well, it'll always be, it's connected to a robot, and so we're going to want to, we never have a situation where we're going to be looking at the beam coming right out of the laser, but it's a lens-on laser is what we're really worried about. So, with this robot, what if it stops here, shoots the beam out for some reason? What's the irradiance, or what type of barrier would I need for a lens-on laser application? And this box right here is where we would get that information. Okay, that's about it.